Alright, time for another DraftPhysics.com video presentation. Yeah, so today we'll deal with Huygens Optics again. We have attempted before to make a video responding to some of what he says about photons. As the title of his channel indicates, he's interested in photons. And in the past, I found some reason to disagree with his interpretation of the evidence and make counter arguments to the arguments made in his videos, and but it doesn't really go anywhere. But I'll keep making, I can only do my part of this internet thing, this communicating thing, this science thing. And I think part of science is debating and recognizing that there are counter arguments. And, he commits, in my opinion, the crime of sort of saying things like, there's no other possible explanation, or a particle model can't do that, or something like that, when he can't rule out those possibilities because he hasn't even, in my opinion, probably thought about it that way. Alright, so the context for this newest video, it's not a great title. Coherence and Light Part 1, Temporal Coherence. It's just such an obscure aspect of what photons do, whether they can be coherent sources or incoherent sources. So I don't know if that will trigger too many people. But he's really making an argument here that it has persuaded him to move not from being a particleist. I mean, I would say he was never a Newtonian, or he would have called himself Newton's optics. What he was a dualist, in the sense that he accepted the fact that it behaved like particles. So he has now migrated to asserting that the truth is that waves can be particle-like. So I would argue it's kind of obvious that in the universe there's push and pull, and you can say, well, the push is really easy to understand, the pull elementally is almost impossible to understand. So you can understand how pushing can create the illusion of a pull, but you can't really make, the illusion of a push out of, oh, it's really a pull. That doesn't work. And I'd say the logic for wave-particle duality is just as obvious, in the sense that it's easy to model how particles can look like a wave, because the ocean does it every day. It's particles of ocean. It's pretty much, I'd say, impractical to attempt to turn wave theory into discrete laser beam particle theory. It just doesn't work. But ironically, that's what he's defending. It's that somehow he's got an interpretation that has migrated him from being understanding that it might be possible that it's particles looking like a wave, to now being quite certain it's waves looking like particles, which I don't find very convincing. Now, he does some very nice experiments, but again, I think he interprets them wrong. So I don't know, I don't know whether it's valuable to go into the past, what he's argued, but it sort of is. He did a video called the real double slit experiment, where he did it under a microscope, which, really isn't the real experiment. And you could point out how he wasn't really seeing interference patterns. He was seeing what happens when you put something in and out of focus. I mean, if anybody's used a microscope, you kind of understand the focal length is all that really is. And it's a little tiny distance where things are in focus, and then everything's out of focus. And what happens with lenses when things become out of focus, you could argue. And that's really what he dissected, was a focus phenomenon, that doesn't have anything to do with photons interfering and all of that stuff. But anyway, that is a separate video, so maybe we'll just play some of this. I want to try to make this video brief, but I don't think there's any way you can really discuss these subjects in 5 minutes. So I guess I won't even try. And so people who are interested are either they're going to have to accept that the conversation has to have a little bit more to it. But anyway, so I should be able to just play this. Just fix the volumes here. This might be too much or too little. Can't really tell until I make the video, unfortunately. But anyway.
Today I'm going to be showing you that light is actually made out of small little particles.
Some of it's due to just the photons hitting the surface.
From Planck and Einstein, we learned that light comes in discrete packets of...
No, this guy just so irritating. So anyway, jeez. So I've played all of these videos just about, right? And pointed out the huge flaws in them. This Young diagram of a double slit experiment is completely a fake because it doesn't get even right answers. It's not a double slit pattern that's created, it's a single slit pattern because the openings are so small that you basically take a 4-source experiment and turn it into a 2-source. You need 4 sources to create the true double slit pattern. If you're going to see the 2 patterns, the envelope pattern and the, whatever you want to call it, the primary pattern, you're only going to see that when you allow 4 sources to make the contribution. And that's the mathematical truth, and that's the truth, and that's the truth. So the Young drawing of the double slit was really the Young drawing of a single slit. And it only works mathematically as a single slit experiment in the sense that the 2 surfaces of the 2 sources are turned into 1 source. So you really just have a 2-source experiment. Okay, continuing. And they all make this mistake. They all call this perversion, this distortion, they all call it the double slit experiment because they were using these infinitesimally small slits that basically create the same source. If you put 2 light sources really close to each other, they can't create interference. There's no possible mechanical geometric way for there to be constructive and destructive interference because the 2 sources are so close to each other they can't create lines that are a wavelength of difference.
energy, called a photon.
That means that each photon should have...
I mean, it's just so bad, these terrible animations. It's just so bad because this isn't describing the reality. It isn't showing what's really happening. This isn't about a thing going through an opening. It's about things going near surfaces. And it's so obvious, and it's so Newtonian in the sense of just recognizing what Newton did with changing the size of an aperture and changing the pattern. And what happens when you make an aperture smaller is that you're increasing the likelihood that the photon will go near the surface, and the bigger the aperture, the less likely. That's why you don't see any pattern when you have a big opening. It's because 99.9% of the photons don't go anywhere near a surface. I mean, there's lots of easy deduction to do here.
decide whether it's going to go through one slit or the other.
Yeah, so this has nothing to do with the pattern. What slit it goes through has nothing to do with it. It just has to do with the surfaces cause all of the bending. The stuff bends because when it goes near a surface, it's plowing into electrons. The photons, when they hit an electron, change their direction. It's that simple. It's just scatter from sources. The simple explanation works really, 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 really well. This complex, silly explanations always end up creating dilemmas, logical dead ends.
Now, how could they interfere with each other because they're...
This was one of the biggest fakes, was the Veritasium one, in the sense that he did the experiment this logical way. Like, I only want one photon in the experiment, so I'll have a really weak source of light, and I'll do the experiment over a long period of time. So then I can guarantee that only one photon's in the experiment. And it didn't work. And so he had to keep narrowing and narrowing and narrowing the amount of time he was doing the experiment in. And coincidentally, okay, when he made it 5 minutes instead of 5 hours, it worked. And he says, well, mathematically, I can still assure you there's only one photon in the experiment. But that's all based on his assumptions about how big a photon is. So it really meant nothing as an experiment because he basically just cheated the whole principle.
There's only one in the device at any one time.
Well,
Yeah, says you. And again, and you overtly admit that no, the likelihood is there's more than one because you had to make the experiment happen over a shorter and shorter period of time, meaning all the photons happened in that 5 minutes instead of 5 hours. What's the likelihood that there's going to be 2 photons in the same place if I take all of those actions and have them happen in 5 minutes versus have them happen in 5 hours? Well, it seems pretty likely that I'm going to have 2 photons in the experiment at the same time.
to quantum physics.
We now have to accept that light obeys wave-particle duality, meaning
So this guy, I don't even know why people think this guy is a somebody, this Dave, the whatever, because frankly, it's mush. Yeah, really bad.
it is both a particle and a wave at the same time.
Oh yeah, which is just nonsense, okay? I mean, that's not even what they're saying, okay? They're just basically saying, well, for some experiments it looks like a particle, and in some experiments it looks like a wave. That's as far as they can logically or, fairly go.
Confused? You should be.
Yeah, baby talk, yeah, it is. Nobody's really analyzed it. Nobody pays any attention. They don't even, like I said, none of these 2-slit experiments that are on YouTube actually show you both patterns. I mean, I'm always saying none. I mean, some obviously show the patterns, but they don't have any analysis of the pattern. So the current physics theory has really no explanation whatsoever for why there's a double maxima and, in the single slit, and why in the double slit there's an envelope pattern. They have zero explanation.
Hey everyone, I guess I was confused. In the past I've assigned particle properties to light.
So let's, I mean, I don't think it's fair. You were never a particleist. You were never a Newtonian. Okay, your argument was still always wave-based. You called the channel Huygens Optics. Huygens is famous for being a wave advocate, one of, you could argue, the first advocates for a wave theory. So come on, you're you just converted from being, a Methodist to being a Protestant. You didn't make any real conversion here.
But apparently I'm not the only one. So why is everyone confused? Well, to find out, let's start by looking at history and see where most of the confusion about particle-wave duality originated from.
Alright, whatever. I don't think there's confusion. I think there's just really bad theory. Okay, and then there's really good pieces. Here and there's little sentences where you can gain an awful lot, and it's in a field of noise. So you could just argue there's a bunch of noise regarding what the truth is. And what you're going to do is highlight a gigantic piece of noise. The Young double-slit experiment is noise. It's not information. He didn't do an experiment Newton hadn't already done in the first place, in the sense that Newton had already done impediment and opening. He'd already done the 2 versions of the single slit experiment, the 2-surface experiment, right? 2 surfaces for an impediment, 2 surfaces for an opening, all right? But he hadn't figured out that, well, yes, overtly it's about the surfaces. Now, I think he knew it was about the surfaces, but I don't think he could write you up a theory about how the surfaces are causing the effect. But it's clear that's what was easily deduced, is why are these 2 things creating the similar patterns? Well, what do these 2 things have in common? 2 surfaces.
Whether light was a wave or a particle has been the subject of fierce debate since the end of the 17th century. When Christian Huygens...
So there was some rather fierce debate on kinetic energy, and it didn't produce the right answer, because the debate wasn't about actual facts, and so that's the whole problem. I would argue that back in Huygens' days and Newton's days, they really watched what each other did, and they tried to repeat what each other did, and so there was some integrity to when arguments were made. And then after Newton is when that kind of went to hell, and it was just about show experiments, tricks, gimmicks.
Huygens published a paper on the wave theory of light in 1690. Most scientists of his time did not agree to his views, among which was one of the most prominent scientists of that time, Sir Isaac Newton. In 1704, so about 14 years later, Newton...
Yes, 14 years, so it's quite a long time after. So I'm sure some people were impressed by Huygens. Huygens was well respected and well known. And, they're all, but yes, and all they have are experiments they've done, drawings they can show, explaining a phenomenon. But obviously they can't model every possible variation of a potential model of even what a corpuscle would be. Is the corpuscle the whole photon, or is the photon a pile of corpuscles? That was the key thing missing from the conversation. And ironically, it's in what Einstein says, so I was a little surprised that Einstein did have it right. He gave you a really close to good description of the reality, and I'll just point out a couple of the little flaws in but otherwise it was really close to getting it right.
He published a book in which he explained the behavior of light in terms of small, fast-moving particles. And for about 100...
Right, and they didn't have laser beams back then, and so there's a lot of reason to think it was possible that light is, something, this wave and some ether and all this kind of crap, because they didn't really do all the energy stuff and the rest of it. But I think logically somebody can understand that if you have some spreading wave going out, that requires energy, and that water waves die. Things die because they're consuming all the energy. They can't go, they can't travel billions of light years across space, if they're dividing into new particles and covering new spaces. If the energy has to be spread over larger and larger distances, obviously the energy would run out.
100 years, both the particle and the wave description had their own fan base. However, in 1801, Thomas...
So this is the famous tragedy in physics, where somebody provided it looks like, scenario, and it has nothing to do with it. There's no point in comparing photons to water waves. They're not the same mechanism, it's not the same, and again, he did it in such a way as to create a diagram that didn't even mathematically work. It didn't even get right answers. Not for the double slit, anyway.
Young demonstrated that light behaves like a wave.
So he didn't do any such thing as any even cursory analysis would demonstrate why it doesn't work. These drawings don't work. They don't produce the right answers. They won't predict the pattern. All I have to do is make this opening bigger, than a few wavelengths of light, and I've already broken his analysis. It won't produce a correct answer.
That the colors of light are in fact related to wavelength. And he did it,
which is really good, fine, great, but Newton had already done that anyway, in a sense. I mean, it was already implied.
This by performing what is now generally referred to as the double slit experiment. Again,
so it's not the double slit experiment if you make the slit so small that there's no distinction between the two surfaces. So the point is if you think of the surfaces as being point sources, obviously if two point sources are really close together, there's no capacity to see the difference between them. They become invisible as two separate sources.
And about 60 years later, the work of James Clerk Maxwell showed strong...
So again, there's no waves in Maxwell's theory. So again, it's the fact that he believed in an ether and he believed it was waves doesn't change the fact that his drawings basically show you very straight line vectors. The lines of force are straight lines. The lines of force are laser beams. The lines of force are something going from point A to point B, and it doesn't spread over point C, D, E, F, G. It doesn't do any of that stuff. So to argue that that somehow Maxwell's math is wave math, I think is unsustainable, unsupportable, undefendable. There's no waves in the math. There's vectors all over the place. The math is covered in straight line vectors, geometry. The whole geometry of the math of the double slit experiment is a bunch of Pythagorean geometry. You're using angles to decide the length of the sides of a triangle. I mean, the whole thing is covered in vectors, not waves.
Evidence that light should in fact be an electromagnetic wave. So at the very beginning of the 20th century, there really wasn't much debate anymore. Light consists of waves.
And in a very incoherent, nonsensical way. We have these magically two different kinds of fields, and one of the fields, like, they draw it this way, but the fact is one of the fields is incredibly weak. You know, the electric field is so much more powerful than the magnetic field, and they don't draw it like that. And waves in what? I mean, what's waving? And how does it wave in a straight line? And how many of these little lumpy waves do you need before you have something that's a photon or not a photon? And then you get into the whole subject of polarization. Does that really have to do with the amplitude of the wave? Well, no, because the real relationship is between the frequency and polarization. Increase the frequency, you increase the polarization, the size of the polarization. I mean, higher frequency, smaller polarization. And what does polarization mean? That means how much surface are you actually going to hit with the light. That's the resolution of your little beams, your little vectors. Okay, so the whole point is what's the huge distinction between ultraviolet light and infrared light? Well, the fact is the infrared light is big and the ultraviolet light is small in terms of all the energy is hitting a smaller surface. Less surface is being hit with the same amount of, you could say, bits. So it's like having cannonballs that hit one single part of a castle versus cannonballs spread over a whole bunch of the wall. You can sort of understand that if the cannonballs are hitting a smaller area, that they're likely to do more damage in that area. That if there's some possibility of breaking a hole, you're going to break the hole by hitting one spot with repeated hits rather than hitting a whole bunch of area with scattered hits. The more scattered your energy, the more displacement it happens over, the less impact it's going to have in terms of creating a product.
So where did things get confusing again? Well, in 1905, Albert Einstein wrote a now famous paper on the production and transformation of light.
Right, and it was based on a whole bunch of these other experiments that were done with cathode rays and this analysis of this idea of a black body radiation and the fact that you could cause electricity in metals by exposing them to light. So Hertz actually made a giant contribution in terms of figuring out that besides this radio wave stuff, what was being transmitted when you had these bursts of energy was light that you couldn't see. And that it was photons that were creating the induction effects were being created by physical photons, light that you couldn't see.
In this paper he combines experimental data from various sources, connects them and discusses some of the theoretical consequences.
Right, good. That's a very good description. Now the quote from Einstein is just, I didn't realize,
And one of his conclusions is that the energy contained in light is not continuously distributed in space, but as he states, it consists of a finite number of spatially localized energy quanta.
Right, so you didn't have the word photon yet, that wasn't in use, and but it's just this idea that the whole idea of a photon spreading over distance doesn't make any sense because doesn't conserve energy. So in Einstein's reasonable opinion, that's a kind of almost a non-starter. If you're not going to conserve the energy, that's not a rational system. It's not a rational model. So that's what the first sentence is basically saying in a polite way. Okay. And so then he's taken, let's just finish the quote.
He proposes that these quanta are indivisible and can only be absorbed and emitted as a whole.
Right, so now that's the mistake. But this idea, okay, distributed over an even ever-increasing volume, but consists of a finite number of spatially localized energy quanta. So that's the big reveal, is that I didn't realize that Einstein had, in fact, properly understood that the frequency of a photon, okay, was in the fact that these are the quanta and there is a distance between them. So, you know, he's saying in very simple language, this is what's traveling through space. This goes at the speed of light, this pattern. So blue light does this, okay, and red light would do that. And that's the distinction. Now it gets more complicated because you have to add polarization, okay, where these are all moving parallel, but they have a polarization. But that's really about how something lands on a surface. So the key is that what you're really doing is pushing electrons in the end. You're affecting electrons. And the argument I would make is that what you're doing on a surface is adding energy to electrons. You're tipping them over, so to speak. You're hitting them while they're moving. So the first photon, the first bit hits, causes motion in the electron. The second one hits, pushes more energy into the electrons. The third one hits, pushes more energy, and now you finally have enough energy to escape the atom. And that's the photoelectric effect, is the fact that you're taking these repeated events and you're adding to the system. So it's like a pendulum swinging, and the idea is you always want to add the energy while the pendulum's going away from you. If you try to add the energy when the pendulum is moving towards you, you'll just defeat. You won't add any energy to the system. So if you want to add energy to the system, you have to hit it consistent with its resonance, or consistent with the idea that its motion might be periodic, and that you need to hit it while it's moving. Now the obvious is that if you are tipping something over and you hit it and it moves to this location, and before it can spring back you hit it again, well obviously then you're going to be able to tip it over. But if you allow it to start moving against you, then you're not going to be able to tip it over. And it's that kind of a simple argument about how photons, okay, trigger an electron event. They trigger it because the energy is added to the system at the right frequency, the frequency consistent with how that electron will be pushed, and how you add energy to its oscillation. All right. And so the real key thing is obviously bits that are closer to each other, closer together in terms of frequency, you could fit more energy in the same amount of time. So this needs a big amount of time, this needs a smaller amount of time. So that's one reason why you would say this has more energy. And the second reason I'll argue is that this hits a much smaller surface than the bigger photon. The bigger photon hits a big surface, the small photon hits a tiny surface. That's why this is more effective at pushing electrons, is because it's more likely to be adding resident energy, where the bigger photon doesn't really have a hope because it starts the pushing process with the first bit of quanta but ends up hitting against the motion because it doesn't hit behind it, it hits ahead of it, you could argue. So I think that's, particles can certainly explain the phenomenon, and Einstein, I think, was correct in understanding that it's light quanta, okay, energy quanta, that's a key word, and that this idea that there are these little bits in the universe, they are identified by anything we call a force. And unfortunately, I mean, if Einstein just put it a little bit together, he could understand that gravity is essentially this force. That gravity is just another form of this force, okay, but it's not in a consistent pattern. So it doesn't affect electrons because it doesn't come at a frequency, a consistent frequency. All right. So enough of that. We'll go back to the video. Hopefully.
And the arguments to support his claims are mainly based on the results of an experiment that is now better known as the photoelectric effect. To understand how Einstein came to his conclusions, let's take a quick look at the essence of the photoelectric effect and what exactly points to quantization of radiation.
Alright, so I'd say that the double slit experiment actually is even more good evidence for particles, because it can be understood that the effect is just about scattering these little bits and then recollecting them. So you're breaking photons and then remaking photons. So maybe I'll make that point. So I think I'll break here and draw that reasoning, just to demonstrate that the photoelectric effect gets more complicated, because you're basically using the movement of an electron, the action of an electron, to understand the action of its cause, what caused it to move. Now obviously the electron is a clump, so in some sense you're using a clump detector and then saying, well, what can I detect with a clump detector except clumps? Of course everything's going to look clumpy because I'm looking at something that's clumpy. I'm saying, what does the clump do, the big clump? And so everything's going to look like it was caused by a clump. So I don't think it's as good a piece of evidence, because basically you're using a clump detector. So yeah, it's not a surprise you detected clumpiness. Alright, so let's try to do a semi-brief description of the double slit. So the idea is you have a single slit or a single impediment, and they essentially create the same pattern, which is just going to be bars and not too much pattern. I mean, the center one will be twice as big, and that's about the only distinguishing feature. And this distance mathematically is the distance deciding what it looks like in terms of, these vector lines that you'll draw, and you'll get this wavelength of difference, this full wavelength versus a half wavelength. Half wavelength is an off, full wavelength is an on. And it's all about this, okay, base to the triangle, and it's going to decide how many of these things there actually will be. So it's, this was always explained to me. They kind of pretended this was an infinite pattern, that just went forever, that you could have photons going in and out, and it really isn't. So the real pattern really does create an arc where the bands actually do get bigger as you go further out and smaller in the center. And that's what the pattern's really doing. So there is no infinite on-off here. There's just a big blob, okay, at this degrees. And you can sort of understand that the distance is really, you're just taking, this distance and comparing it to this distance. And whatever you have in here, okay, how many wavelengths you fit here, this is going to decide exactly how many bars you have on this 90 degrees of arc. So you just double this number and you'll get the number for the total pattern, because it's really just creating two separate patterns in the two separate directions, but no point going into that. And so those are the two surface experiments. All right, so it's about surfaces, not about whether there's a single opening or not. It's not a single slit experiment, it's a two surface experiment. And so Young introduced the idea, all right, of a double slit experiment, but he introduced it in this kind of fake manner, in the sense that the way he was doing the experiment really just created the single slit, because these surfaces were so close to each other that they couldn't create triangles. You couldn't make a triangle with this small base. If this is just a wavelength of light, this base, you can't create two lines with the different distances, the wavelength of difference in the distance of the lines. So you can't have constructive and destructive interference because the two point sources are too close to each other. So you have to have the further distance. Now, this pattern, this arrangement, if opened up, does create 4 sources. So if you have these slits wide enough, what you essentially have are 4 point sources. Okay, 4 places from which you can derive a possibility of making a photon. And that's all you're really doing, is taking the 4 sources and say, do the 4 sources add up to a photon, on or an off? So you're getting an on or an off, and that's really the geometry, is when these sources match, that is the 2 outside versus the 2 inside sources are in phase, you get light. And when they're out of phase, that is 2 of them don't match the other 2, these 2 sources aren't in phase with these 2 sources, you get a dark. So you need all 4 sources to make a contribution, or let's just say 3 of the 4 sources to make a contribution to get a light, and otherwise you get a dark. And that's sort of the distinction between the double slit, and again, the double slit pattern is distinctly different in that it's made up of light, okay, in a distinct different pattern, in the sense that you have these distinctive offs. So you essentially have 2 patterns in the pattern. So you have the little bars, which represent something obviously of a higher frequency or something, right? I mean, why the little ones here, and then you have this bigger pattern. And what that really represents is, in the double slit you have these 2 outside sources. Would obviously, this is the biggest distance, this is a gigantic distance. That distance means there's a lot of wavelengths inside that big giant difference, and that's creating the small bars. And the smallest distance, the closest 2 surfaces are, they're creating the envelope. So the big pattern is being created by the small distance, and the small pattern is being created by the large distance. So another simplification way of looking at it is, if I was to bring 2 slit experiments together, that is, okay, I had 2 single slit experiments separated, and I was to slowly bring them closer and closer, what am I really doing? I'm not bringing 2 of these distances together, you know, and this distance here and this distance here isn't what I'm bringing together. What I'm bringing together is this distance out here and this surface out here. These 2 is what I'm really moving together, and then this distance here I'm moving. So what I'm doing is creating new sources. I'm taking 2 separate 2 source experiments and I'm turning them into 1 4-source experiment. That's why the pattern looks the way it does. And I would say the obvious and simple explanation is, this is just about surfaces. What happens on surfaces? Surfaces are covered in electrons. The photons hit the electrons. The electrons are jiggling, so the photon moves based on the jiggle. And it's deflected in any one of these possible directions. And the highest probability being straight, and the lowest probability being 90 degrees. Very low probability, probably. There probably never is a photon way over here at the 90-degree mark. But anyway, you're just scattering the photons at the 4 sources, basically breaking the photon, and you have a 50-50 chance, okay, that it's either going to land going back in phase or land going out of phase. It can't do something else. There's not some other option. There either is going into being in phase or there is going out of phase. There's no other choice. So all you're doing is taking the bits, breaking them, and then just remaking them into photons again in different locations. And so all of the fringe light, all of the pattern created here, all of this pattern, everything outside of this very bright center, all of this light, all of it, is created by light that went by the surface. The photons that went by the surface make all of the pattern. The ones that don't hit a surface, don't go near a surface, just go straight through the experiment, or are blocked in the case of the impediment. Alright, so that's probably enough of a primer on the 2 slit experiment, which demonstrates, in my opinion, provides a mechanism completely conducive to a particle explanation. So in spite of their assertion that no particle model can explain, yes, a particle model can explain. They just don't want to hear the explanation. They didn't want to look for it. They really didn't challenge themselves to find it. They just presumed it dead. Like no explanation that doesn't include God can explain reality. That's all their assertion is. It's beyond the mechanical system. The mechanical system can't explain. When, yeah, it can. Okay, it doesn't take that much work to provide the explanation. So back to the photoelectric effect, which is a much more, in my opinion, complicated because of the different things there's different factors that are creating the effect. So as I pointed out, we're saying the photons can have different length in the sense that red light has fewer elements in it than blue light for the same amount of time. So in the same time, the two have a different amount of energies. And the other argument is that the blue light is going to hit a much smaller area of the surface than the red light. And it's those two factors that are creating what are the apparent energy differences. And it's only an apparent energy difference. It's not a real energy difference.
Experiment is generally performed in a high vacuum with 2 electrodes. One of the electrodes is covered with a layer of a specific metal, for example cesium. And when we irradiate this metal with UV light, electrons can be expelled from it. We know this because we can measure the potential difference that arises between the 2 electrodes. Basically because the negatively charged electrons go from one electrode to the other. And so we can do various experiments on this system, like vary the wavelength of the light while measuring voltages and currents, or deliberately change the potential to see at which field values the flow of current stops.
Right, and the other part to this to recognize is, alright, should be back, system crash and such, so somewhere around here is where we left off. So you can vary the frequency of the light, he says, and obviously that's a huge factor in this experiment, is varying the frequency of the light.
Voltages and currents, or deliberately change the potential to see at which field values the flow of current stops.
So you're really just saying is, there's two things they especially test for that are interesting to them. Yes, how much does frequency affect it, and then how much are the electrons, with what energy are the electrons leaving the surface. So the idea is you can make the electrons leave the surface very fast or less fast, and that there's a threshold for the amount of energy you need to get them to leave at all. So the frequency decides not only whether they leave, that is, there's a threshold, you have to be a certain frequency or you can't even get them to leave. And then there's the second factor where the higher the frequency, once they're leaving, the faster they leave the surface with more energy.
Now the thing is that this phenomenon only occurs when the frequency of the light used for irradiation is above a certain value. For example, the effect exists for UV light, but not for visible light or...
So let's understand it exists for all the light above that standard, and he only sort of used a little bar here, but that's really not how it works, because it's really this line that goes up. So if you use X-rays, you get very energetic electrons, and they leave really easily. So, the line it progressively increases, which was really just saying, again, if you're trying to tip something over, if the thing is going to oscillate, there's a time when the speed at which you're hitting is faster than any possible return. So you hit it, it's still moving in the direction of your motion. It still hasn't even stopped moving. And you hit it again, and you hit it again. So obviously the sooner you hit it, so when it first gets hit, it goes 50 miles an hour, and then it's going 40, and then 30. It's like going up in gravity. It goes slower and slower and slower. Well, if your boost phase is you hit it, and then you hit it again so it's going 50 miles an hour after you hit it, then it's going 49 miles an hour, and you hit it again. If the faster it's going when you hit it, the more energy you're adding, obviously. So the quicker the rate at which the frequency is hitting, obviously the thing it's hitting doesn't have any time to slow down. So you're really adding the energy. Each hit provides a full boost because you haven't lost any energy, with any rebound. There's no rebound and there's no decline in your velocity. I mean, if you hit something that's going 10 miles an hour with 50 miles an hour, then you're only going to get 60 miles an hour, right? But if you hit something that's going 50 miles an hour with another 50 miles an hour, then it's going to go 100 miles an hour, that kind of thing. You're adding the energy. And if the quicker you add it, the more efficiently you add it. That's sort of what I would take. That to me is the rational conclusion to draw about why there is this line saying you have to be at least this much energy to get the thing to leave. Remember the fact that the faster you hit it, the higher the frequency, the more efficient the energy is that goes into it, so the more energy it keeps.
Infrared light, not even if the intensity of the latter radiation is very, very high. When the frequency of the irradiation is above a specific threshold.
So let's understand the frequency. The problem with the red light is it's hitting a surface, what you call a photon. The places where the energy is hitting on the surface are further and further apart. So the polarization is also playing a factor. I would say the polarization is what's creating that limit. If you could get the red light to have a smaller polarization, that is, if you could somehow create red light at a smaller polarization, then maybe you could get the effect. But because the red light hits a higher density more surface over a larger amount of surface, it can't bore the hole, so to speak. So it's like the difference between a laser beam that's focused and unfocused laser beam. Okay, so one that's spreading out and hits the target with a big dot has less energy, won't burn a hole, where if you can make the dot smaller and smaller, it will burn a hole. Kind of just that simple a description. It could be that simple, is all I'm saying. They never even consider polarization as part of the argument, but polarization really is saying the higher the frequency, the smaller the location on the surface, all of the energy is landing.
However, we can measure the effect even at very low radiative power. By changing the potential difference between the two electrodes, we can also measure the maximum kinetic energy of the emitted electrons.
So the kinetic energy is just a lie, so again, we're not going to go into that crap, but I mean, it's just the energy. They shouldn't say kinetic energy, it's just, they should say it's, it's momentum, frankly.
And it turns out that this maximum kinetic energy is dependent on the frequency of the light and increases with higher values.
So just saying what I just said, basically, yes, that the higher the frequency, the more energy is transferred to the electron.
So now we're faced with the following. We observe emission of electrons, so discrete entity.
So the idea here is that somehow this energy is hitting a single electron. I would argue it's not how it works. The electrons are all in a matrix, and when you hit one electron, you move other electrons because they all hate each other. So when you hit one electron, you move other electrons. Those electrons are the ones getting hit by the next piece of radiation. They're the ones getting boosted. So you push one electron, then you hit an electron that was pushed by that first electron, and then you hit a third electron that was pushed by that electron. So whether it's 2 hits or 3 hits or 5 hits, who knows? But eventually you get the electron to a high enough speed where it leaves the atom. It acquires escape velocity, put in simple terms.
These from the metal by irradiation. And in order for these electrons to escape from the metal surface, each of them needs a certain amount of ionization energy, which is more or less...
So it's just energy, it's not ionization energy. So, again, I really hate this rhetoric. Now, I would argue that there is some question whether electrons do any of this, okay, in the sense of leaving a surface, and that what they really are doing is shooting ions off the surface. And that's what you're really transferring is nucleuses, atomic ions. You're not sending single electrons, but whatever. We'll continue.
Constant. But apparently they're also left with a certain kinetic energy, which is dependent on the frequency of the light. And this suggests that the total energy needed for this is...
So it's obviously the total energy needed is to acquire escape velocity, and you can escape with extra energy. You can go 700 miles an hour. Say you only need 500 miles an hour to escape. Well, yeah, you can go 700, or you can go 800, 900. You'll escape, and then you'll have this extra energy as you leave. So if you have just enough energy to escape, then you escape and you move very, very slowly away. But yes, if you have more than escape velocity, then you can leave very, very fast after you've escaped. But it's really just all you're saying is how fast is the electron going, and that speed has built into it escape velocity and the extra that you gave it.
Supplied to the electron as one discrete package with a certain amount of radiative energy. So part of it's used to escape the metal, and the part that's left over remains as kinetic energy to the electron. And so the experiment strongly suggests that light consists of small chunks of energy rather than a continuous stream.
Alright, so it's really not just a suggestion. I mean, mathematically, Einstein did a whole bunch of mathematical analysis of how there's really just, it fits the model to understand that the energy density we're just averaging energy. And so the whole energy of the system isn't what we're talking about. We're talking about the specific areas in which the system is being disrupted. I don't know how it's really hard to explain the distinction, but you're just basically saying that the system is being hit by each little piece of quanta doesn't have any more or less energy. It only depends on what that photon is. Okay, whether the collection of the energy is dense, being high frequency, that is a lot of it in a small area of time, obviously that's more efficient at transferring energy. So the closer in time I can put the little quanta, the more efficiently they transfer energy. That's sort of the mathematical analysis.
Now, it's these energy quanta in light proposed by Einstein that are referred to as photons by many people today.
Alright, so obviously Einstein stated right in his statement that he's not calling it a photon in the sense that he's saying a photon is made of energy quanta. So it's a composite object. So Einstein understands it to be a composite object. Now he says that the composite object has to stay coherent in space. Now that's a mistake, because all you have to do is create the same pattern. So what you're really doing is saying a surface can create dot dash dot, Morse code. And then it can break that code, send just dots and dashes randomly, or spread out. And the surface can actually receive dot dash dot or dot dash or dash dot dash. The surface can receive all kinds of different patterns based on the scattering of the original signal. And that there are certain rules about how much of the original signal will survive that breaking. And that's all that this is about. Is a pattern starts at a surface, the pattern can be broken, that is rearranged, but its energy is still there. So if photographic film, polarizing film isn't blocking any photons, it's just changing their phase. And by changing the phase, you're breaking the pattern that's going to hit the surface. But all the bits, all the energy of the photon is still getting through the film. And all you're saying is by doing certain things, by putting a third film in or doing something else, I can fix what was broken. And I can get back the photons that you don't see now. The ones that are landing just as heat, rather than landing as light.
You might now think that the name photon is an invention of Einstein, but it's not. The name photon was introduced 21 years later by Gilbert Lewis, who used it as the name to describe a hypothetical new atom that plays an essential part in every process of radiation. And
so obviously that's not really relevant. I mean, he's not describing a photon because he's calling it an atom. But obviously photon as a word works. I mean, because you have all the other photon, electron, proton, neutron. it fits, but it really has to be understood that you're not describing a singleton or a single, you're describing a pattern that hits a surface, a pattern of quanta, as Einstein would say, light quanta.
I guess that's how it sticks in everybody's mind, including mine. A photon apparently being some kind of light particle.
So again, that's the just, frankly, the sloppy language over time. We're all taught that we're supposed to be thinking about a photon as a single object, and that somehow the single object has a frequency, and all kinds of nonsense like that doesn't work, because Einstein's actual statement isn't put on blackboards in schools, and where he just points out that it's made of numerous quanta.
Yes, partly also because of the name it was given by Lewis. Electron, proton, neutron, photon. The corpuscular or particle view on light, reintroduced by Einstein, still causes a lot of confusion and influences fundamental.
So again, that you could just argue that your side is the one creating all the confusion. Throwing waves in this here is just totally unnecessary. The double slit, single slit can all be understood as scattering these little bits and just rearranging them. There's no constructive and destructive interference. There's just broken photon, remade photon. Okay, so there's just a reconstructed photon or a non-reconstructed photon. That should be the terminology. So frankly, your side is the one. Your wavical people are the ones that have made the noise and made a mess out of something that's really simple. Newton was on the right track, and you took the track wrong. Okay, both on energy, creating Leibniz's mv squared nonsense, and then on photons, going with the Huygens Leibnizian wave crapola. It's all on you, creating the noise and the deceptions.
Fundamentally, how many of us look at light. Drawings of emission and absorption processes show discrete little wave packets. Complex.
So again, wave packet, this is all your jargon. It's totally unnecessary. It's certainly, you want to call it a package of frequency or a pattern of frequency. That's being more, in my opinion, explicitly correct. That's telling the truth better.
Experiments with light are explained in terms of photons moving through slits and prisms and then hit.
Right, and lots of people talk about single photon experiments, and it can be explained they're not single photon experiments because they're using an opaque filter. An opaque filter is basically a bunch of slit experiments. It's a diffusion filter also. So anytime you're using an opaque filter, that is, you're trying to obscure how many photons get through it, you're also creating a diffuser. So you're making the light come from different locations and leave in different different directions. So you're diffusing the light when you're supposed to be just, creating an impediment to its progress. You're doing a lot more than that, because you're changing the direction of the light. So a piece of a photon that was going that way, okay, can be made to go that way, and one going this way, and the two of them can meet in the same location and create the dot dash dot pattern that's necessary, the frequency that's necessary. So quanta from different sources can end up creating the photon. Just in the double slit experiment, you're creating a photon that looked like it went straight through, but it really didn't. It's a piece of a photon from over here and a piece from over here, and those two pieces came together at the right location at the right timing to create the illusion of a photon that went straight through.
Detectors. Stimulated emission is described in terms of light particles, one photon in, two photons out.
Okay, and it's drawn as if these photons would have the same frequency when, of course, they don't. So that doesn't work either. But this is, in the laser context, you're really not talking about one photon in. You're really talking about the fact that you've created a potential where any energy you hit the system with will create more apples. So you could throw an apple at an apple tree, and you can make more apples fall out of the tree. So you throw one apple into the tree and 5 apples fall out of the tree. So that's all you're really saying here. You have to add energy to the system. You have to make the apples ready to fall.
Corpuscular description of light is literally everywhere, and almost every science video on
So this is such a lie. I mean, it's so every single video on YouTube is about some sort of wavy crap, okay? So they draw it as a particle and then they wave it all over the place. So as soon as it goes through this thing, it's going to turn all into wave crap. So it's just, to me, it's just such a lie to talk about how these videos on YouTube are defending particle science, because they're not. It's all covered with Huygens and Young and all of that crap. There's no Einstein analysis. They don't show you a photon in the Einstein description, which would be a numerous quanta at a frequency. That's not the model shown.
YouTube is about light being a particle at some level.
No, it is. And the particles don't split in two and they don't recombine. So again, that's just nonsense. That's how they pretend particles don't work. They make particles ludicrous.
But is it correct?
Yeah, is that a particle that just flew out of there? No. Yeah, not even close.
In this video and the follow-up video, I want to leave the corpuscular or particle view behind me and try to explain light.
So he doesn't really have a corpuscular view. So again, he calls the channel Huygens Optics. Get real. Huygens was all waves, no particles. You know, so it's a misimpression for him to say he's a reformed particleist. He's not. He's now just doubling down on the Wooey wave theory.
And its properties purely as the result of wave phenomena. The reason I made this video is that hopefully it can lead to better understanding.
So again, there's no fundamental wave dynamic. You have to create an ether, you have to create a medium, you have to do all this crap. You have no infrastructure defining how a wave in what. There's no elemental wave reality, just as there's no elemental pull. Elementally push works. Elementally particle works. Wave does not.
Initially for myself, but of course also for others. Personally, I do think that the energy in light is in fact discontinuously distributed in space.
Right, and that means that the pieces of light do not have any tie to each other. So unlike water, okay, the light isn't a bunch of atoms that are stuck to each other. The light isn't uncompressible. Light isn't a lot of things. It is compressible. You can change the spatial relationship without applying any effect on the entire field of photons. I can destroy, I can move, I can do anything I want to one element, one quanta, one piece of light quanta. I can do anything I want to it, and it's not going to magnetically or electrically move all the other photon pieces, all the other quanta. Localized energy quanta. Again, we're talking about energy quanta, which as a collection makes a photon. All right, and so Einstein is saying which move without being divided. Now that's the part that's wrong. Okay, of course you can divide them, you can separate them, you can move them. So that's what the two slit experiments are doing. You're passing these energy quanta through a field of electrons and you're scattering them all over the place. And then on the other end, they'll land either in phase or out of phase. 50-50 chance. Okay, and which can be absorbed or emitted only as a whole. They have to create the pattern. So you have a pattern, dot, dash, dot. You have to have a pattern landing to have a photon. It has to land, dash, dot, dot. It has to land with the frequency. The bits have to hit the surface with the right pattern. If they don't hit with the right pattern, there's no photon. There's still energy. There's still heat. There's still gravity. There's still whatever you want to call it. But there's no light photon in the sense that you won't have a light photon reaction. You can't add energy to the pendulum if you're adding the energy when the pendulum is swinging towards you. That's all it's saying.
As Einstein initially concluded. but not because light itself consists of packages or photons, but because of a direct result of wave phenomena, in particular those related to coherence.
Alright, so I don't think we're going to bother going through this coherence argument because first of all I don't think it's very persuasive. So this just has to do with the regularity of the waves. So you can have very regular waves, all the same size, all the same humps. And then you can have waves that are, where the frequency changes. That is, like in the example of dropping a rock in water, the waves are more compact, and as they spread out, they get larger and larger and larger, so they're incoherent. So you can have coherent sources and incoherent sources. And I really don't see how you can demonstrate how we must believe in waves by using coherence. It's just not going to be relevant. So he's going to use an interferometer. He's going to show a pattern in the experiment. Maybe I'll show that part. So yeah, let's do the interferometer part. So we'll skip all of this coherence stuff because I don't think it's terribly relevant and go right to the experiment.
Do you want to cut the plate quickly? Try these electric drill shears. Put the sawtooth on the electric drill. It turns into...
As a
Isn't it
consequence,
bizarre that they can't find like real people to actually describe a product they're selling and like have a computer voice do it or something? I just find that just amazing. They can afford to buy a commercial, but they can't afford to have somebody who can actually read their little tiny paragraph of crap, proficiently. It's very surprising. Alright, so he's proving here that the light is coherent in the sense that he's from any distance he's got a little white light that he's put through a cumulating lens to make it as parallel as possible, so it creates a little laser-like spot. I mean, it's obviously not a laser beam in the sense it's not focused and it's not very bright and all that stuff, but it stays consistent. The spot doesn't get substantially larger with distance.
the light from this source looks kind of weird because it's very parallel over long distances. Now, with this spatially coherent source, we can look at the temporal coherence properties of white light.
Alright, so again, he's just really just talking about coherence in two directions. So what he's done is made it very coherent in terms of it's very parallel, but he doesn't necessarily have frequency coherence. That is how much red or blue or green light's in there. It doesn't have to be consistent.
Here you see the camera image where the length of the two arms of the interferometer are exactly equal.
Okay, so he says so. That's the first thing I would say. Now, this pattern, okay, as soon as you saw it, I say, oh shit, that's the pattern for thin film interference. The straight line bar type pattern. And it's always, that pattern is created by creating a tilt. So maybe I'll draw that. I mean, I actually, have a video of some of that somewhere. Well, maybe I'll make a follow-up video, especially if he responds to any of this, which is unlikely, which is really, it's very discouraging that none of these people will interact with any of the critiques of their statements. They can just make them, and they really don't have to account for them or defend them, and they're not willing to do any of that, which is, clearly, I'd say, a character defect. Alright, so you can, this was another Mike Young thing I learned, where you can put a solid piece of glass on top of another piece of glass. Alright, and if you just drop it, it'll sit on a piece of dust, and you'll actually end up with an angle. And the angle will create exactly that pattern across this surface of the glass. The glass will get that pattern. Alright, and the higher I make the distance here, that is, the bigger the piece of dust, the tighter the bar pattern, alright, and the less that piece of dust, then the pattern almost can become non-existent. It's such a big, giant pattern between on and off. It's really big bars. So the thickness of the bars is decided by how big an angle this is tilted at. So in doing his interferometer experiment, he's sending something in, and he's using a cube splitter, so he's not using a single piece of glass as the splitter. And so, as I've pointed out before, this whole idea of beam splitting is sort of a canard. In the sense that the two beams are never going to be equal because you're doing something distinctly different to the two beams. And the difference is well, especially with this beam splitter, you're clearly the division between these two sides, these two prisms, is a thin film. This is a layer. This is two layers being forced together, creating internal reflections, blah, 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 blah. Well, anyway, the idea is that, yes, you have it go through both surfaces, hit the mirrors, and then you're going to see the image over here of it. I should draw that in the opposite color would probably be helpful. And then the returns will come in, from the two sides, and then they're going to be doing this interference. So one of the beams is going to represent this surface, and one of the beams is going to be representing essentially this surface. And he actually points out how he has tilted this mirror. So he's not reflecting the beam back straight, he's tilted the mirror, which is exactly what this is, which is why there's a pattern. So this isn't a traditional interferometer at all. It requires a completely different analysis. Now I saw that too, 5 years ago or whatever. I did these experiments on my porch, and I found that all I had to do to change the bullseye pattern I was getting, was turn the mirror. I didn't have to move it forward and back. All I had to do was change it, just a tiny change in how parallel it was, made a change in the pattern. So it wasn't so much about this perfect distance thing, it was about angles. And again, he's getting this thin film pattern, which indicates this is about the angle of the mirror, not the distance of the mirror. And the more he increases the angle of the mirror, the bigger those bars will get, and the more consistent with the angles of the other, the flatter he gets, he'll get no pattern.
We can observe a clear interference pattern. Now, getting this image is not trivial because the accuracy...
See, it's really not an interference pattern. Thin film is really just about an internal reflection, and the fact that you're creating two sources. You're creating one source further away from the other source. You're getting a wavelength of difference. So in different locations, because it's gradually changing its distance, you can see that you have a wavelength of difference, and then you'll have two wavelengths of difference, and then you have three wavelengths of difference, and then four wavelengths of difference. So you're just progressively showing that exactly what you would expect, which is you are increasing the wavelength, and the bars and the spaces are so much more precise than they are in the double slit experiment, for example. They're not changing size, they're not doing all that other stuff because the distances are tiny. The wavelength of light is the distance you're measuring, and you're just progressively going from 0 to 1 wavelength difference, 2 wavelengths difference, 3 wavelengths differences.
Required for matching the two path lengths is only a few wavelengths. This is because the light is spectrally broad and the contained frequencies will go out of phase very quickly.
So it's just saying he's using white light, so he has a bunch of other light mixed in with to create the white light, and that they are going to create their reflective point. The point at which they're a wavelength of difference is a different location. So that's all it's just saying, that this distance is 2 wavelengths for blue light. Well, red light, it's 3 plus 4. You know what I mean? So depending on where you're going, they'll match in some places, and then you'll restore the white light. And in other places, they're clearly going to be at different points where there's a full wavelength of difference.
The reason that we observe an interference pattern is the following. If the arms of the interferometer are equal, every electromagnetic wave from one arm, regardless of frequency or phase.
So again, it's all about these waves. They're not waves, it's a frequency. And you could just say the frequency at returning is either in phase or out of phase. So it's just about whether or not the two signals are in phase or out of phase. It's not about waves. It's 2 binary signals. I can just send 2 binary signals to a device, 2 electrical signals, 2 pulses. I can have pulses that are in phase or pulses that are out of phase. A particle model perfectly can explain that. There's no reason for me to be obliged to believe in your wavicles.
Is basically in phase with the wave from the other arm, and therefore this will lead to visible constructive and destructive interference.
Right, so the frequencies either line up, this one's on, they're the same place, this is the on place, this is where the little ball of Einstein's energy quanta would be, or the quanta can be a little bit behind, and now they're not in phase when they hit the surface. They're not going to hit the surface at the same time. More importantly, in this case, they're not going to hit with a pattern, which is dot, and then little time later dot, and then a time later dot. And that's what needs to happen for electrons to be, to add energy to electrons. To add energy to electrons, you have to hit them at their resident frequency, the frequency of their binding energy. Their binding distance between each other will tell you what frequency you need to hit the electron with to make the electron gain energy or momentum.
Around the point where the arms have equal length. And the reason why we can observe this pattern directly from the CMOS sensor is that the two mirrors in the interferometer are slightly tilted with respect to each other. And this
So again, that has nothing to do with the CMOS sensor. That has to do with whether or not you're going to create a pattern or not. And the fact is now you've created the cause of the effect. The tilt is the cause of the pattern.
causes the interference patterns due to temporal coherence to spread out over the CCD sensor area. You can
So again, it's not about spreading out over the area of the CCD. You didn't have a problem because these beams aren't going to be that small anyway. So no, you're just creating the cause of the effect, and it's the tilt of the mirror that's causing the pattern.
You clearly see how the different wavelengths start to go out of phase quickly when we move away from the point of equal path length. In fact, by using
and that's only because of the colored light. So they're not changing. So if you use monochromatic light, you'll get dead perfect little straight lines here, all in the same location, all the same distance, equidistant. It'll be a very regular pattern. I probably should just play that video, frankly, so maybe I will. Alright. Pause for a moment. Didn't realize, yeah, I covered the video. Anyway, sorry about that. So you can just see the pattern here, and he's talking about how this is changing and it's spreading, and it's only happening because, yes, the different colors are spreading. That's a known phenomenon, blah, 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 blah. And it wouldn't happen if you used monochromatic light, which he's not using for this experiment. Later he will. Alright, so anyway, I'll get to the other little clip just to show the similarity. Alright, this should work, hopefully. Alright, so he's got one piece of glass on top of another, and he's just pushing on it to show that if I put some pressure on it, I can squish that piece of dust.
So I changed it a little bit there, and you can kind of see.
Now I pick it up and drop it again to see what kind of pattern it gets.
Probably just added dust instead of took it away.
So now they're a little wider
Yeah, so there's a little
than
bit
originally.
But if I could smash it all the way.
Alright. So I think it makes the point. So if you could smash it all the way, there'd be no pattern, effectively. It would lie flat and there'd be no progression of wavelengths of difference. They'd all be the same wavelength, they'd all be in phase. It would be either all black or it'd be all white. I mean, everything would be either all in phase or all out of phase in terms of the internal reflection. The reflection between the two surfaces would be either all in phase or all out of phase. So it'd either be all white or it'd be all dark, if it wasn't for the fact that it's tilted. Alright, so that's the print I wanted to make. And yeah, so we'll go back to this.
narrowband interference filters, we can look at the separate frequencies or colors present in the pattern. We see that every frequency has its own interference periodicity. The blue light.
Right, so that's something everybody would expect to see, is that yes, the blue light is closer together, the green, the red is the furthest apart, and the spacing and the size, and that's why it looked a little bit ugly, was merely because you weren't using monochromatic light. But if you use monochromatic light, you'll get a very even pattern, because you're really just measuring the tilt of one of the mirrors. Alright, so that's probably enough. I mean, I don't know if there's much else to be gained by getting into this coherence argument, because I don't think it really demonstrates anything. But at least might as well just play a little more.
Light with the shortest wavelength has the smallest spacing. The red light with the longest wavelength has the widest spacing. And the white light interference pattern is basically the sum of all frequencies or colors. Now here's a screenshot again of the interference pattern that we observe. If we now discard the color information of the camera for a moment and just look at the intensity, the image will look something like this. This image allows us to extract approximate intensity information and plot it as a function of distance. And you see that.
Alright, a huge flaw in this is obviously it was just getting blurry and blurrier because the bars are in different locations. So it would have been much better to just take the blue pattern or the red pattern or whatever and just analyze those single elemental patterns, because then you would have gotten a very consistent reveal. Here you're just saying, yes, of course they're closer to being less out of phase. So in the center they're less out of phase. Further out they become more and more out of phase. So the more times you do the pattern not matching, the blue not matching the red exactly, it gets further and further and further spread out. So I mean, to me that's just obvious. That obviously, yes, you're going to have tighter coherency in the center because you haven't doubled your error and then tripled your error and then quadrupled your error. Yeah.
We can now very roughly estimate the coherence length of the image. With the average wavelength of the light being around 500 nanometers or half a micron, the coherence length of the white light is just about 2 wavelengths long, so about 1 micron, extremely short.
And again, it has nothing to do with the coherence. It's it doesn't mean anything. You're mixing different frequencies of light. Obviously, it's not going to make a very good pattern. And if you don't mix them, you'll get a very consistent pattern. So it's just about how many frequencies you've mixed. The more frequencies you mix, the noisier the pattern. I mean, kind of a duh statement. Alright, so I don't know if I'll just finish it off.
Okay, now let's try a different light source, in this case a laser diode. Now stimulated emission only takes place at very high field intensities in the laser cavity. In other words, at relatively high operating powers. However, if we operate the device at very low currents, it basically works like a normal LED and only shows spontaneous emission. So let's take a look at both operating modes using the Michelson interferometer. We'll start out with a low operating current. The diode now operates as a normal LED, so no stimulated emission. And here you see the camera image again when the two are.
So what it's really revealing is that it gets better at producing one frequency the higher the intensity you run it at. So the higher the intensity, the less. What this blurriness on the sides is representing is the fact that this isn't all one red number. So it isn't just 500, 500, 500, 500. It's 520, 515, 517, 555, 575. So there's a mixture of different reds in the red, and that's what the blurriness is indicating. And he's really just saying that somehow this is meaningful, and I'm going to say, no, of course, that would be exactly what you would expect. More than one frequency, it's a mess. One frequency, it's nice and clean. I mean, it's sort of obvious. The multiple frequencies mean you're going to create noise in the image.
Arms of the interferometer are set to equal length. In the images, the interference lines are spaced much closer together, and that is because I placed the two mirrors in the interferometer under a larger tilt. So we can look at decoherence.
Right, so exactly what I stated, the higher, the greater the amount of distance in that pitch, the more bars you create, because you can create them more quickly. Right, the higher this angle, the bigger this angle, the more wavelengths of difference I can create because I'm creating more distance to create them in. There's a greater amount of back and forth distance the higher the pitch. The lower the pitch, the less distance. So you're creating more opportunities for a wavelength of difference by increasing the amount of space between the two surfaces. You could argue the space between the surfaces is really equatable to the travel time of the photons. The more travel time for the photons, the more opportunity for a wavelength of difference.
Coherence over a larger distance. You can now observe that coherence extends over a larger number of wavelengths. We can do the same measurement of coherence length here. We can take a screenshot.
So this is only because the bars are closer together that it looks less, that it's cleaner for a longer period of time. So, but it's obviously there's more bars in the same amount of distance. So you're just, where it starts to go bad because of the numerous frequencies isn't per, frequency. I mean, it isn't per instance. It's, a gradual distance, an actual distance that they're getting further and further apart. So the closer they are, the less distance they move, the less blurriness you get per amount of distance. So the fact that he's changed the resolution of the two images is the only reason why these two images have a different number.
Of the interference pattern, convert it to an intensity plot, and then estimate the coherence length. And now it's almost 4.5 microns, which is about 4 times longer than in the...
So the coherence length just means how the same distance apart from the center of these peaks. The center of this peak, where are they the same distance apart and where they become further and further apart? And that's what he means by their coherence.
Case of the white light from the LED. Now let me show you what happens if we increase the current through the laser diode to the point where it actually starts to lace. So here I'm turning up the current. Because the intensity of the light output is much higher now, we either need to decrease the shutter time of the camera or attenuate the light by means of a neutral density filter. But look what happened to the interference pattern. Now suddenly it's everywhere. Whereas in the previous cases it was tricky to find the interference pattern, I can now go wild on the micrometer of the linear stage and never lose the interference from sight. We can actually extend the difference in distance between the two paths from centimeters up to several meters. This can be achieved by carefully setting the current of the laser diode to a value of very stable operation.
Right, but we already know that the tilt in the mirror is what's causing the interference pattern that you're calling an interference pattern. But it's really not an interference pattern, it's a recombination pattern, but whatever. Alright, so I think this is about the end of this video.
And so this illustrates the extreme difference in coherence length between a source operating in spontaneous emission mode and stimulated emission.
Alright, so it really doesn't do that at all, because all you're really saying, the reason why it's coherent is because you have less dirty light. You have more light at the same frequency, and that's it. So there's less noise in the signal. That's it. There's no other reason that you're getting a better pattern here.
Mode. In the latter case, the source can evidently create a spectral distribution so very narrow that coherence...
As he moves it closer, further away, he's going to get the same pattern, but he's changing where the bars actually are. So you can see them shifting as he turns. They're shifting their position. They have exactly the same distance between each other, just as in the double slit experiment. The distance between the nodes has to do with the frequency of the light. It has nothing to do with, how far away the distance is or how many wavelengths of distance there are. That doesn't change how the size of those little bars. So that's, I don't think he's using a logical progression here in this deduction.
This is preserved over distances of several meters, which is 1,000,000 times longer than in the case of spontaneous emission.
So again, spontaneous emission means dirty, lasing means clean. One more likely to be of smaller and smaller, 500, 501, 502, 503. Nothing more than that. The other one, 520, 550, 570. Okay, very big range in terms of frequency. And then here there's a very low range in frequency.
So, I want to pause my presentation here, and I will continue in a second video, in which I will, among other things, discuss spatial coherence in more detail. And I will of course continue the discussion on how phenomena related to coherence and interference can create a non-uniform distribution of energy in space.
Okay, so it's really not a non-uniform distribution of energy. This is just the fact that you're creating either a clean signal or a dirty signal, and that has nothing to do with photons and their function. You're not getting to a real element of understanding the foundational function of a photon and what it actually represents. And I would argue what it clearly just represents is a signal, a pattern of energy distribution, and that's it. There's nothing else. It's made out of a very simple elemental function, a quanta of energy, and it's just how regularly, with what pattern you put the energy onto a surface will decide whether you see a photon or you see heat or you see nothing. And such. Alright, so anyway, so it should be a video. I'll put the pieces together and hopefully we'll have a video. And such. So this has been DraftPhysics.com, debatephysics.com. I'll put this video in the two slit category, the wave particle. We'll maybe put a second label on it. And we'll see if we get any reasonable conversation or counter argument. We'll see. Yeah, I've done my part. Let's see if the rest of the world can do theirs. And so yeah, I can get rid of that. So till the next time and such and so forth and whatnot.